ואם זה נשאר באותו מקום?
לא, כי זה אומר שכאילו תלוי בתנאי התנועה.
אז 2 כן, נכון?
כן, אבל זה לא אמיתי. היום דיברתי על זה עם...
זהו, אז איך זה לא קורה שם?
זה רשום עדיין, אבל לא חושבת על הלוח.
שואל פה, נו.
כאילו אני לא הצלחתי, ואז... יאללה, יצא לי משחק...
I asked if the heating is working.
Do you want it to be or not? That's the part. I'm pretty sure
Definitely
it was on and we turned it off.
could remain top.
זה כאילו בתרגול, המשפחה של הקונספציה,
לסדר שלא נחסום. זה שלי.
אז גם 3 וגם 4, גם לא.
מכירה שאתה יודעת, כאילו אני על 4 גבוהה, כאילו לא עשיתי גם שני תפקיד. אבל 3 דברים פשוט, כאילו עשיתי סתם פעולות
ששמתי את זה פה, גם אחרי זה, זה שיצא לאט.
Okay, so we're still dealing with second quantization. And as we have seen in the previous lecture, basically the idea is we have a single particle basis, and perhaps I didn't emphasize in the previous lecture, but it doesn't matter what basis is it. Could be a solution to a Hamiltonian, could be any other orthogonal basis. Okay, so I have a single that has some states, and the many particle state is described by how many particles do I have in every state. Okay, what else did we see? We saw that basically, can someone tell me what is a many particle, not really, what is in this type of representation? If I have only one particle, how do the basis states look like?
1 and 0.
Exactly, I'll have all the possible combinations of 1, 0, 0, 0, 0, 1, 0, 0, 0, so on and so forth. If I have n particles, n1 plus n2 plus n3 plus should be equal to the total number of particles. Okay, and then we discussed how to construct such a state, and we defined the vacuum state, which is a state. It's not zero, it's definitely a state. It's a state with 0 particles in it. And creation operator at state I just changes the situation where I have one particle. In this case, no difference between bosons and fermions. Simply to create one, there's no difference between. Okay. What happens if I operate on an existing state that has already electrons in it? Until here, we described in the previous lecture, now new material. Okay, I have some state, and I'm trying to create an additional particle in state I. So here, basically, I have a difference in fermions. What is the result?
If Ni is occupied with 0.
Exactly. If Ni is equal 1, the result is 0. It's an illegal operation. If Ni is equal 0, then I have the state don't have to write Ni plus 1, simply 1. I have the 1. Here I forgot something and I'll write it down now. to remind you, for fermions, okay, so each one of the cases has a small peculiarity. Fermions, I have to worry, is it occupied? And if it's not occupied, I should correct the minus sign according to what's written here. What does it mean? I sum up the number of particles up to position I, and take -1 and multiply it the number of times that I have the particles. For this simple case, I have 0 up to 0, and -1 to the power of 0 is just 1. Okay, for bosons, always I can add an additional particle, no problem. But I have to correct the amplitude before the wave function when I'm adding up another one. That comes for the same reason that you have seen in harmonic oscillator creation and annihilation. You had also this square root. Okay. Annihilation operator. Okay. What happens when Ni is equal 0?
No, n equals 0. Absolute 0.
Absolute 0. It's not a legal operation on the state. In all other cases, for bosons, zeta is +1, so this is not interesting. 1 to whatever power is still 1. But I have to correct the amplitude. On the other hand, for fermions, the only possibility is Ny equal 1, and therefore square root of 1 is 1. But I have here this minus that can come into account. Okay, so that's so actually, instead of writing down this many particles state, I can define it simply by operators operating on the vacuum. what am I saying here? Create whatever number of particles you want in the first state. Just worry about normalization. The same for the second state, the same for the third state, and so on and so forth. If I have nothing in the state, it would be Ni equals 0, no operator. Let's define the number operator.
Isn't it supposed to be in square root, the Ni at the bottom?
I think not, but you can check. And what is the number operator? Well, same as the number operator in the harmonic oscillator, AI dagger, AI, just to get used to using this formalism, I'll check it. Okay, so I'm applying the number operator for state. What am I supposed to get here as a result? Ni, exactly. Okay, so I'm reading off my rule book. AI and of course, I'm working. Order is important. In a moment, I write commutation relations, and therefore, you never change the order without thinking. So I'm first annihilating and then creating. Oh, okay, annihilation. The answer is square root of Ni. Si okay, creation, here I have no problem switching them because these are numbers. Okay, so I read off the result. Ni plus 1, but here I have Ni minus 1, so it's again square root of Ni. And since for fermions zeta to the power Si is 1, I don't care writing it again. Okay. This gives me Ni. Whatever, if it's if it's minus 1 to the power 2 times Si, what is the result?
1.
1. So it's not relevant. So I got the same state multiplied by Ni, which is the meaning of a number operator. Now you could stop me a moment and said, okay, 1 minute if ni was 0, so I couldn't do this step. No problem, then I would get immediately 0. Fine. Okay.
Can I ask a question?
Sure.
What happened before the last thing that you wrote? What happened to zeta si? Okay, but why is it gone?
Excuse me? Because I'm multiplying it twice.
Yes, but the next you didn't write it as it's a
So this is minus 1 to some power.
okay.
So usually I have to worry.
Okay. Oh, we're talking about fermion.
And if it's bosons, I don't
Yes.
have to talk at all,
Okay,
because then it's
okay,
1
okay.
to the power of whatever.
אני גם יכולה לשאול,
Sure.
אבל כאילו הוספת חלקיק בצד השני, אז זה לא צריך להיות SI פלוס 1.
Okay, that's an important point because I perhaps didn't emphasize it enough. Let's just bring it back. So all the states up to the one I'm playing with. Okay, so all these states didn't change. So it's the same power. Life becomes interesting, and that towards the end of this lecture we'll see, when I'm annihilating a particle at one point and creating it at a different state. Then things change, of course. Please.
Why do we have this term?
Which term?
The -1 power of s.
Because this exactly has in it all the nature of fermions and bosons. The difference between fermions and bosons. And give me a couple of more minutes and you'll see exactly why. So I'm defining a general commutation relation for fermions and bosons. Okay, let's see what we get in each case. Okay. So we Okay. What is this? This is a regular commutation relation that you're familiar with. Okay. So that's usually called commutation. And this is known as okay, and it is also sometimes using the following notation. So those are different notations. I can't, well, actually most people don't use this notation, but use the square and curly brackets to define. Square brackets is minus sign, curly brackets is a plus sign. Okay. So what do we get from these commutation and anti-commutation relations? Okay, as usual, I'm looking what they do when I operate them on a state. Okay, and for simplicity, I'll divide it to bosons and fermions. Okay, so for bosons, minus AJ actually, I want to keep through the space for finishing that, so I'll first do bosons and next I'll do fermions. Okay? So, what happens here? Okay, I'm using the usual rules, nothing beyond it. Okay? The first term annihilates a state at AJ. And according to the rules that I have, lighting gives me square root of nj. Right? Then I create a state at ni. since order here is not important because this z to the power si doesn't play any role for bosons. Okay. Questions? What did I ignore here?
When I is equal to j.
Exactly. I equal to j. So, okay, let's see what happens then. Okay, in this case, write it explicitly. Okay, I just wrote what I'm going to do. So, the first term, I'm removing here someone from N1, and I'm getting here square root of Ni. And then creating it again, so I get another term of square root of Ni, and I get N1. Okay? Okay? So the commutation here would have given me -1. And if I would have chosen AI and AJ dagger, what would have I received?
1.
1. Okay, so basically the result of the commutation for bosons is delta ij. It's a plus or minus 1 according to the order. Okay? Not very surprising. Always, if the commutation is between different operators, ai and aj, it's always equal to 0. If it's between operators that are operating on the same state, then I have either plus or minus 1. Let's see what happens for fermions. So I'm continuing. Okay, now I know already that I have to pay attention I equal to j or I not equal to j. So we'll start with I not equal to j. And okay, I just wrote down the state. And I need so for the first term, I'm annihilating something at nj. Okay? As usual, fermions, I don't have to worry about the amplitudes, but I have to worry about the minus 1 to the power. Okay, so minus 1 to the power summation from 1 to j minus 1. Okay, of this, I sum up all the numbers here. If I have an even number, it's 1. If I have an odd number, it's minus 1. Okay. Ni comes in this case before nj. Could have been otherwise around, but who cares at the moment? So Sorry about it. I'm changing it here to K, just to have a different index here. Until where do I have to sum up?
The I or J.
Well, this was for the J, so the, yes, please. Question? Or? Okay. Okay, what happens here if nj was equal 0? Would have been 0. If ni was equal 1, would also have been 0. Okay, let's look the other way around. Okay, the end result is the same from the point of view of the state. But what changed?
The number that you sum.
The numbers that I summed. Okay, what do I do here? I first create something at I1. So this didn't change. I still have -1 sigma k equal 1I -1 n. Okay. But for the second guy, when I'm going now to remove the guy at nj, I have to sum up on all these states, but here something happened. Right? Because I've already created here a number, and the old ni became ni plus 1. So what's the difference between this guy and this guy?
Always have a first sign.
-1. Oh, everything else is the same. So because of guy, if I compare it to this guy, it has a minus. Okay? To solve this thing, I can go and write here all these summations, but I don't need it. What do I need? Stop a minute and think. Which values could be here?
0, 1.
0 or 1? If it's 0, this guy can create and then annihilate, no problem. On the other hand, if it's 1, this guy can create and this guy can annihilate, right? So it will be always equal . Okay. So from this exercise, first I did it just so we'll get used to using the definitions here, because anyone who's working with fermions has always to pay attention to this. It's very important. It would make a huge difference in the result, not taking it into account. And second, we see that for either the bosons or the fermions, we had to define the commutation and anti-commutation relations in order that we'll get this delta ij. Otherwise, we wouldn't have gotten the result. Okay, so great, but now you can come and tell me, look, I don't like this basis lambda. I want to work with a different basis. Am I allowed? Yes, of course. The basis is my choice. I choose it according to my convenience. The physics shouldn't change if I change a base. So, how do I do it for the usual single particle bases? That one we know, or we are supposed to know. All this is single particles. Can someone tell me what I'm doing?
Many particle?
No. I'm still asking about single particles. How do I transform the base? Fourier is for one particular base, which is the momentum base, or the K base, but could come up with trillions of other bases.
You need to compute the outer product?
Inner product, but
You need to
Yes.
project.
algebra, linear algebra. As long as both the basis lambda and lambda tilde are orthonormal, this is correct. So all I need for transforming from one base to a different base in single particle representation is to do simple transformation, Unitarian transformation, for those of you who are impressed by Cold. Okay, so how do I move from base to base? In many particle physics, first of all, the important thing to understand is what is special about the many particles base? Just a number representation on a single particle base. Okay, so what I have to do here is basically, when I'm transforming from one base to another base in single particles, I'll have to transform the creation and annihilation operators. And then I can construct a new state in the new base. If you want, I could just give you that and do complex conjugate on that. So instead of creating at a state lambda, I have to create with a certain amplitude on a combination of states in lambda prime, not prime lambda tilde. Okay, let's see a concrete example using actually your Fourier transform. Let's say that the two bases that I'm handling is a usual position base. And K-space. Okay, two well-respected single particle bases. If you're really picky, you can start worrying a bit. Well, the space is continuous, K is also continuous. We Here we have summations, but you know exactly what one has to do there. Instead of summations, what do I have? Integrals. Okay, so we're not impressed by that. And just for concreteness, I'll assume that we are dealing here with a finite region between 0 and L. Can always at the end take L to infinity. The reason I'm doing it because what will happen to K in this representation?
Diverge.
No,
Discrete.
K doesn't will be discrete.
Yeah.
And life is always easier in discrete, so prefer to stay discrete in K representation, and if I need at the end, I'll take L to infinity. Okay. So I have here two respectable creation and annihilation operators. Creates a particle in position X, annihilates it in position X. Sometimes in literature you'll find that this way of writing, I don't like it, just not to get confused with the usual writing of psi. And now you can see from where the term second quantization came into account, because I have it looks as if I have the same wave functions on my psi's, but now they're operators. So to avoid confusion, I'll keep creation and annihilation here always as A, and I know that I'm working on X or K just by what's written here. Okay. So how do I write these operators in K space? Okay. Okay. Up to now, I just copied the definition and exchanged the summation by integration. Could do the opposite transformation. Same I could do for the annihilation. Or I can take these and just complex conjugate.
Could you remind why the inner product is e in the power of ikx?
It's noisy. Could you raise your...
Could you remind why the inner product of x and k is e in the power of ikx?
Okay, so the simplest way to remember this, okay, up to 1 over square root of 2 pi or whatever. Okay. So I'll write in, sorry, I'm messing here. X k. Okay. Set up. Okay. What do I do with single particle operators? Life is very easy and very straightforward when I'm dealing with a single particle base for which this operator is the basis of this operator. Okay. Let's say I have some operator have some operator theta and I have its basis. Okay? So I have a set of eigenvalues, theta 1, theta 2, theta 3, that correspond to the eigenvectors theta 1, theta 2, theta 3. Okay, this is single particle. So I'm talking about basis for which theta I is diagonal. Now someone comes and tells me, okay, I'm writing down many particle state for this single particle basis. Someone can tell me what is the result of operating theta on this state from physics. In a moment we'll get it from mathematics.
Sum of the eigenvalues.
Sum of the eigenvalues.
Those כפול מצב.
Exactly, times the occupation. Okay, so it should give me n1 times theta 1 plus n2 times theta 2, whatever. Okay? Because each state which is in an eigenstate of the operator, and I'm just counting how many particles I have in this state. That's the many particle operator that gives me this result. For this, what happens if I'm not working in this basis but at a different basis? Let's say I want to describe my wave function in the basis lambda.
ריצ'רד? למה A דאגר והחלפת את זה לתטא ולא ל-I?
I'm just reminding that it's creation and annihilation on theta. Perhaps a better notation would be How did I get it? Just by using the transformations that I have written previously. Nothing more, nothing less. So, if I know the single particle operator, I have no problems in writing it down in whatever basis I'm interested in and operating it on my many particle state. Let's see an example. So the single particle Hamiltonian is given in the usual way. If I'm using the momentum basis, tell me how many particles I have at k state, k equals something, then how many I have at another k, and sum up all the momentas. Okay. If I have potential, well, here my life is much easier if I'm thinking about the position basis. Okay. What do I do when I have the usual Hamiltonian, the ubiquitous Hamiltonian? Okay. So I have to make up my mind. Work in K space or work in the position space. Okay, let's make a choice. Let's decide to work in K space. Okay, so this is fine. Here I have to do something. I have to transform from AX and A dagger X to AK and AK dagger. But we have written it already then. So just insert it, do the integral, and see what is the result. So I'm looking just on the potential part because the kinetic energy part is trivial. Okay, actually, I'll do it the other way around. I'll start here from okay, actually, I'll start here the other way around. I'll write it in the position space. Okay, so just a moment. Okay, I want to start with the position space. Okay, so this is good and lovely. How do I write this term? Well, I'll write down the definitions of AK and AK dagger as position operators. Just wrote the Fourier transforms of these two operators. Good. what did I do here? Well, I'm embarrassed to say I didn't do anything. I just move the summation inside and split this case where to time. At a point, it looks completely meaningless.
How can you combine the integrals together?
I didn't come. This is simply do integral on dx, do integral on dx prime, because this guy doesn't depend on x prime, so I can move it before. It doesn't change anything. Okay, so I'm continuing here. Well, it was my continuous struggle to make a simple equation more complicated. Instead of writing k, I write it as a derivative of e to the power I k x. Perhaps a bit puzzling why I'm doing it, but it's certainly not something that I'm not allowed to.
the derivative of
This is the derivative. Yes, right. Look what what remains here. I'm going back to what's written here. Okay, so another step of complication, right? Except
what is it?
told you that I'm taking a finite 0 to L piece,
A boundary condition.
boundary conditions. Okay, we're almost there. Chronicles delta, yes please. Because I have here, I want a finite 0 to L cyclic boundary condition. So basically, integration here will bring me to the result, and they have to. If I'm taking them to finite, it has to be 0 at the ends, and if it's cyclic, it also goes to 0, because once you're doing over L, you return to the same result. So either cyclic or finite, both of them. So it's not completely correct for finite, because then you should use sinuses and cosines, they're the same idea. Okay, questions about this? Chronicles delta. Okay, so I can get rid of one of the integrals here. And yes.
Is it 0 because the partial derivative is 0, or?
No, because what I'm doing here is again integration by parts. Okay, and what is this result? Another reason. Okay, this is the result.
How did you move from the almost partial integration methods?
Yeah. I could go the other way around, doesn't matter. How would I write the average kinetic energy in a single particle language? I'm given the wave function.
Just without the integral and the creation of
The average.
with the Hamiltonian.
Right? Again, look on the situation here. Looks a similar expression where I replaced psi by creation and annihilation. And now, again, that's the reason that I used second quantizations. I didn't come here and simply replace psi by figure, but looks as if that's exactly what I did. But we did it just strictly by the definitions. Okay, so basically we know in principle now to write down any single particle operator. If I can write it in the basis, very simple. If I need for some reason, like here, to use a different basis, so I write it in the basis that it's comfortable for me and transform it. But I can write down any single particle operator. Okay, but we didn't come here to do many particle physics with only single particle operators. What do I mean by many particle operator? Particle 1 interacts with particle 2. So basically, that's what we'll do in the next lecture. Okay, we'll stop here.
I'm not